This is CPE 233. This is lecture 20. What we're going to talk about here is some preliminary stuff for some later experiments. So what we're interested in namely is the interrupt timing. We'll introduce some new concepts here, which is essentially switch balance and how to deal with it, namely one-shots, and then example. The example is not going to be part of the lecture. It'll be part of another lecture 20 video. This is the state diagram associated with the controlling it state machine. And what this is saying, once again, is to act on an interrupt, I finish the instruction I'm on, which you can see right here or here if it's a load instruction, and then I go in the interrupt cycle. Inside the interrupt cycle, four things happen. And we're going to talk about those four things individually. And so here they are. Essentially, I need to put the address of the interrupt service routine into the program counter. I need to save the old program counter, which I do. These are two registers in the control and status register block. I also need to disable interrupts. So I do this by writing a 0 to the MIE, and then what I want to do is copy that MIE bit to MPIE. And obviously, when I get an interrupt, the MIE bit's going to be 1, so a 1's going to be copied to this bit. So if I want it disabled, I need to if I want it re-enabled, if I want it to exit the interrupt service routine with the interrupts disabled, I need to turn this bit off. So when I'm returning from an interrupt, what I'm going to do is take my saved address and put it into the PC, and then what I'm going to do is copy the MPIE bit, which is bit 7 in the CSRM status register. I'm going to copy that to the MIE. So what this has the ability to do is it saves the state of the interrupt service routine enable bit into MIE, and then when I exit the interrupt service routine, it restores that state back to MIE. If I don't like that, I can go change MPIE under program control as part of the interrupt service routine. So this is the interrupt taken timing, and so what we have here is an instruction, and this is not a load instruction because I don't see a write back state there. But the interrupt turns on right here, but it's really not acted on until the end of the execute cycle of this instruction, which is the last cycle of that particular instruction. Had it been a load instruction, this would have been happening after the write back cycle. So at the end of the execute cycle, it sees that the interrupt is set, so it goes into the, at the end of the execute cycle, it sees the interrupt is set, it goes into the interrupt cycle, one state, four things happen. Now, we'll see how many of those things we can see here. So MTVEC is this. It was previously written. It gets written to the program counter. Here's the program counter. At the same time, I'm taking the address of this instruction. We didn't execute this instruction. This would have been executed had we not taken an interrupt, but that's where I need to come back to. So I'm going to store that in the MEPC, which is good. You can see the MIE automatically turns off, and additionally, this MIE is written to the MPIE. So all four things are demonstrated there, and that's it for taking an interrupt. When I return from the interrupt, I need to do two things, and one of those things is to take this M, and let's get this right somehow, is to take this MEPC value, which was the instruction we would have executed had we not taken the interrupt. We're going to put that into the program counter because that needs to be the next instruction we execute. That's one thing. And then I'm going to take that MPIE bit and copy it to MIE, which has the function of re-enabling the interrupts. And essentially that's it for returning from interrupt. You can see there's an MRET instruction there. It's just a normal instruction, nothing fancy about it, 2 cycles. So there are some issues regarding the interrupt signal. Exactly, it could be too short. If it's too short, it's going to be missed by this timing diagram. That signal has to be there at the end of the execute cycle. Essentially, has to be there at the end of the cycle before the new fetch, the fetch of the new instruction. So that's a way of saying it that covers both normal instructions and load instructions. Also, if the interrupt's too long, it could go through this thing, go through the ISR, and then have that same interrupt generate a new interrupt. Okay, so there's an issue there. And so what we want to do here is kind of deal with real world issues, and length of the signal is one of those things. But also, you know, if I'm going to connect a switch or a button directly to the interrupt, I'm going to have problems with it in that there's something called switch bounds, and what I need to do is clean up the switch bounds. So the switch bounds, ideally, this is what you think your switch activation, how's that look like? Anyway, it doesn't look like this. It will actually bounce for a certain amount of time, and then it will settle. So the idea here is, this is ideal. This is what really happens. But what I need to do is ignore all this stuff, because this looks like at the nano speed of microcontrollers, this looks like it got 5 or 6 interrupts, and it didn't. What you want is this. So I need to put a debounce circuit in there to debounce this thing. Debouncing is very simple. It's activated when the debounce circuitry sees that it goes from 0 to 1, which it sees right there. It waits. It waits for this long, and at this point it checks to see if that bit is still a 1 or not. If that bit's a 1, then that was a valid button press. If that signal is now a 0, then that was just noise, and we're going to ignore it. But this is the result of a valid button press. So switches and buttons, they actually do have switch bounce. I'm not making this up. And what it's saying here is bounce time 10 milliseconds. What that really means is it's guaranteed, the output of the switch is guaranteed to be stable after 10 milliseconds. Heck, the thing may not bounce at all. May bounce like 1,000 times, you don't know, but it's guaranteed to be stable after 10 milliseconds. And so yes, what we're going to do is fix this. We're going to accomplish this with a debounce circuitry. And the next experiment, which is experiment 8, you're going to use debounce circuitry, which is provided for you. So the pulse width, once again, they can't be too short. If it's too short, that signal won't be there at the end of the execute state or the write back state for load instructions, and you'll miss it. If it's too long, it will come around again and generate a second interrupt from the same signal, which is generally not what you want. So the next thing I'm going to do to this thing is to make sure this interrupt is not too long, is tie it to a one-shot. So here's the debounce. It's been debounced, but here is the one-shot. Now the one-shot is a circuit that when it sees a transition, it puts out a pulse, but the pulse is of limited width. And so even though the button remains pressed, the output turns off. So if by using a one-shot, I'm not risking having the same interrupt generate, two traverses of the interrupt service routine, etc., etc. So anyway, this is the filtering. I already got rid of the debounce, but now I'm going to put a one-shot on it. That's going to make this signal, and I'm going to connect this signal to the interrupt. And it gives me the ability to craft it so it's long enough to be caught, but not too long such that it can be caught a second time. So trivia question, a one-shot is known as a monostable multivibrator because it has one stable state, and that's we'll go back here. That's this state. This state is the stable state. This state is an unstable state. And so what else here? A stable multivibrator is an oscillator, like a clock signal, and a bistable multivibrator is a flip-flop. Remember that for your next interview. So the question here is how fast can I enable interrupts after an interrupt is taken? So this is kind of important. I think it's pretty important because the issue is that is it possible to disable interrupts under firmware control? And yeah, it is possible, but it won't work in every situation. So what we want to do here is have the hardware automatically disable the interrupts. So essentially, so the firmware doesn't need to deal with it. And that prevents the same interrupt signal from being processed twice. Okay, so what else here? What's the minimum interrupt pulse width to ensure the FSM will catch the interrupt? And we'll see that in a second here. And what's the maximum time an interrupt pulse can be to ensure the signal does not generate multiple interrupts? So let's look at these diagrams here. So this is a timing diagram that shows how fast I can possibly turn the interrupts back on. And so it's going to take the interrupt. The first instruction in the interrupt service routine is going to disable the interrupt. It's going to re-enable the interrupts. The interrupts got disabled automatically in hardware. I'm going to turn them on in firmware. So how fast can I do that? Well, it's going to take me 2 clock cycles if the first instruction in the interrupt service routine is in fact enabling the interrupts, which is what this is doing. So that's the answer. That's 2 clock cycles, and you can see that essentially what I've done here is essentially written to this bit directly. Now the way I have this here, if I hadn't written to that bit, it would have been re-enabled anyway when I executed MRET instruction, because the MPIE is a 1. But that wasn't what we were interested in. What we were interested in is see how fast we could re-enable the interrupts. Even 2 clock cycles, the problem being that there's going to be an interrupt. If the interrupt was still there, it would be there at this point, and I would not go to the next instruction. I would go to another interrupt cycle, and that's why we disable the interrupts automatically in hardware and do not rely on firmware control to disable interrupts. It's not going to always work. So there's the answer. It takes 2 clock cycles to enable the interrupts, and essentially, yes, we have to filter these things to make the interrupts work properly. Too short, it's going to be missed. Too long, it's going to be caught multiple times. And that's it, folks.